Today, we will talk about a specific application within the medical device market, which is the characterization of a dental implant. I would like to introduce today's presenter, Mr. Adam Platteis, which is the sales manager in America, and Dr. Carla Sotero, which is application specialist at Sensofar, with an extensive knowledge about this application. We'll split the webinar in two parts. Adam will go through a presentation of the solutions, and then later Carla is going to run a live demonstration. Adam, I think you can start.
All right, well, thank you, Alberto. So thank you again, everyone, for joining us. I'd like to walk you guys through a little bit of what the agenda of the presentation is. We're going to talk a little bit about the company, our general portfolio, and then ultimately talk about some of the dental implant solutions that we offer. We'll have a live demonstration at the end with Dr. Otero and be able to answer any questions. So without further ado, I'd like to explain who we are as a company. And so Sensofar was founded in 2001. We're based in Terrassa, which is just north of Barcelona, and we're a 100% private company. We design and manufacture optical instrumentation for characterizations of micro and nanoscale surfaces. Our solutions are in quality control for QA/QC and R&D. We have a large global footprint with distributors. We are in over 20 countries supported by our distribution partnership. And since 2001, we have sold over 900 systems, close to 1,000 now, in various industries from semiconductor, PCB, medical devices, of course, dental implants as well. Some of you, even on our presentation today, currently do have some of the SNEO systems in your lab. This is our office in Terrassa, Spain. Everything from our manufacturing to software, R&D, marketing, and management is in this building. We also have offices located in Asia, Germany, and where I'm located in Connecticut in the United States. Here we have a overview cross-section of various partners and customer references that we have. There are plenty of customers that we work with as well that because of NDA restrictions we're not able to show, but we are very proud of our latest United States partnership with Worcester Polytechnic Institute. Dr. Chris Brown in the Mechanical Engineering Lab has one of our SNEOs, and he supports and endorses Sensofar metrology. So thank you again to Chris. This is our general portfolio for our benchtop systems. On the left, we have our latest and greatest fringe projection system, the S-Wide. It's a large area system that's able to capture images in fractions of a second and without any movement in the Z range. We had a webinar on it last week, and we're happy to share that with you if anyone's interested at the end of today's discussion. The next system is our SNEOx. This is our flagship system. It incorporates all the technology that many people know is proprietary for Sensofar, being that it is a focus variation, confocal, interferometer are all included in the sensor head. We can also add a reflectometer as well for thin films. The middle microscope is what we're mostly going to be discussing today. It is our SNEOx 5-axis. It's the same sensor head as you saw on the SNEOx, except with the 5-axis, we put the sensor head on a taller bridge design, and then we add the articulating 5-axis arm underneath. The S-Lynx is another model that we have. It is our manual, cost-conscious system. So it still is focus variation, interferometry, and confocal, but with limited capabilities to the SNEOx. And finally, we have our S-Onyx. This is traditionally used for inline interferometry, but here we do have it on a bridge design as well. So again, these are our benchtop systems. And on the next slide, you'll see that many of our sensor heads can be removed from the benchtop, and we can put them into integrated automated cells for inline measurements. So these could potentially go on a gantry stand or even a robotic arm, and we can control our sensors through an SDK. So just a little bit more about the technology of the SNEOX before we get into what our solutions are for dental implants. As you can see, we've had many generations of the SNEOX. We're currently on our 5th generation. These were all the predecessor models that led up to today's version. And we're very proud of the capabilities, as they are unique, and is what I will show you on this slide here. Sensofar is the only company in the world that does incorporate the imaging modes that you see on this slide. Everything from active illumination focus variation. This is what you would attribute to more of a bright field microscope. We're able to capture more surface form that's more into the millimeter range. We can capture slopes up to 86 degrees, and we can also incorporate high dynamic range for any high reflectivity part or any shiny surface that you might have. Sensofar also has a confocal scan ability for the highest lateral resolution, which is 140 nanometers in X and Y. The confocal is also the fastest scanning aerial confocal in the market. Interferometry is also something that we offer, and we're able to achieve 0.01 nanometer when we use phase shifting interferometry, otherwise known as PSI. We also have your traditional coherent scanning interferometry as well. And finally, as an option, we have a spectrometer or a reflectometer to measure thin films or transparent films between 50 nanometers and 1.5 micron. This is something that we add into the system by using a piezo drive in the Z range. Questions that often come up, and this slide illustrates which samples are best suited for which technology. So here you can have a quick look at what your sample might be like and which imaging mode you might use to image that sample. This is something that we can always discuss with you offline as well. So we use LEDs to illuminate our sample. Typically, ISO allows 3 different ways to achieve confocality. You have a spinning disc, which is traditionally used in biology. You also may have seen a laser confocal system where it's a point scanner that rasters across the system, across the surface, and that's relatively slower compared to what we use, which is an LED microdisplay. So when we use the LEDs, we don't have any inherent noise. We also, because there are no galvo mirrors that have to raster the laser, we have a longer lifespan for the LEDs. They're cheaper to replace, and they also don't have any extensive calibration or service requirements. So it's a much more user-friendly light source compared to a laser. So now we're getting a little bit closer to the 5-axis and what we'll be discussing today. The one thing that we'd like to point out and emphasize is that the 5-axis on the SNEOX is unique, as we're the only system currently offering a confocal for the 5-axis in the market. And we're able to capture the entire surface area of a part by having the carousel swing through the open area at 180 degrees. And with a collet on the center area, we can rotate your part 360 degrees to be able to capture the entire surface area. So how do we achieve that? Again, you see a dental implant here on the right, which on the collet can be rotated a full 360 degrees. And as we rotate the sample, we're taking images, and these are oftentimes complex geometries that we can then merge together and create the full 3-dimensional image that you can capture surface roughness from, or any type of critical dimension that you might have on your part. All right, well, thanks for hanging in there in allowing me to explain the technology. And now in the next slides, we'll talk a little bit about our solutions for dental implants. So just a quick overview. Many of you I know are already experts in this, but there are 3 typical types of implants. The one on the left, the endosteel implant, is what we're mostly focused on with the SNEOs. You can see the screw, and that seems to be pretty typical in the types of implants that we do image. So the endosteel implants are often embedded in the mandible or maxilla, while the middle implant is the subperiosteal implant, which rests on the surface or of the bone beneath the periosteum, and the transosteal implants penetrate the inferior mandibular border. So, but again, we'll mostly be focusing on the screw design. In dental implants, for endosteel implants, there are various different types that are on the market. The zirconia and the titanium are the 2 most common, but as you can see, they have different surface color, reflectivity, shape, coatings, etc. These can all be challenging to be able to capture certain images. So it's good to be able to have a system that offers different imaging modes to be able to handle changing characteristics on your sample. So there typically are many different types of dental implant designs in the market. And that's because dental implant failures still occur. So the typical reason for them failing is because of the lack of osteointegration. This could be because of the status of the bone, the surgical technique used, or the implant loading conditions. But it could also be because of the topographical evaluation, which would be the implant material, the implant finish, or the implant design. There is an intense field currently dedicated to studying the interactions between topography and cell response. And what we've seen is that there is a lack of standardization with the dental implants topographical characterizations. So the ideal surface texture has not been established yet. And this is what customers purchase the SNEOx 5-axis to help develop. When you're taking a look at the topographical evaluation, there's 2 certain things that you can learn. One is the control of how you can manufacture your process, and this works in concert with the performance of the part, or the function performance. So as a user better understands their topographical evaluation, they can learn to control and predict to optimize the manufacturing process and functioning performance. And currently accepted today with using tools to evaluate your surface, 3D optical profilometers offer the best ability to characterize your surface, as your surface is 3D in nature. And by allowing a 3D system instead of what we may have used in the past, which was a 2D stylus profilometer, we're able to capture things such as volume, holes in your sample, porosity, any type of debris. And these are all parameters that typically equate to SQ volume or SDR measurements. These are part of the ISO 25178. Another thing to point out as well is anisotropic surfaces are problematic for 2D contact stylus systems. That's why we do advocate for using a 3-dimensional system. So confocal profilometers and interferometers are the only accepted methods currently able to evaluate densely threaded oral implant designs. We do believe many of you agree with that, as you currently are using our systems. But for those of you that are new to how profilometers work, the future is 3D. So we're happy to further discuss this with you and prove this to you as well. So on this page, we've worked with many dental implant research institutions for many years. Some of you may be part of some of these research groups, but there are various papers that we have as case studies and scientific papers. We're just going to move through a few of them here. If you see any that are of interest to you, we can share this with you and further discuss what the papers are about and see if they're applicable for any of the work that you do. We have a few from University of Oslo here and University of De Leon, Mondragon, and just a few more here. Again, if you would like, we do have these on our website, or you can contact us directly and we'll share them with you. So ultimately, why do people choose Sensofar for their dental implants? For one, we can capture a full 3D characterization of your part, and we are the only company that offers the 3 imaging mode technologies as confocal, focus variation, and interferometry in the scan head. Here we're able to see how we can capture the full outer surface and all the critical dimensions as we can move the profile to any area on your part. So not only can we capture the entire outside of the part, we can also capture the inner shapes, such as the threads, and learn and program the system to be able to image specific points for roughness. You can capture the entire area, or we can program the system just to move to certain areas of the thread to learn what the roughness values are. Here you can see the outer shape completely captured. This took 5 minutes to achieve. And if anyone does use CAD, we have a new partnership with GeoMagic where you can compare your part to the CAD design. And of course, on the bottom right, we also offer SensoMap, which is our licensed version of Mountains Maps by Digital Surf, where you can do any of the extensive analysis on your part. Some of you mentioned that you were interested in the inner shape of the dental implant. Here you can see that we can utilize our focus variation technique to capture the inner walls and geometry. Being able to provide a step height or multiple step heights is definitely possible with this system. We can do any type of linear measurements in X, Y, and Z, and we can capture any of the ferret, min, or max angles that might exist on your part. Again, that can be moved in 3 dimensions, so you can capture any area on the inside. As we briefly discussed, surface roughness is important to many of you, and you can see how we're able to program the system to move anywhere on the part using our confocal system to measure the peak, the flank, or the valley of the dental implant. And we're able to produce the ISO values for ISO 25178 for any of the SA or RA values. So these would, volumetric values are capable as well, along with SQ or SDR. Oftentimes we're asked, how are we sure that we're getting the correct roughness? And this workflow is something that we'll provide for you and teach you how to set up. We can save this as a recipe, or you can apply it yourself in a default mode. But typically, the general guideline is to capture the largest area possible using a 50 or 100x objective. Then the first step is to apply an S filter. What this does is it removes the system noise from your sample. The second step is to provide an F filter to the 3rd order polynomial. This will remove the form of your sample. Finally, as an option, we introduce an L filter. So this is a 50 micron Gaussian filter, and that will remove any of the extra waviness to only isolate the roughness that we're looking to measure. So again, this is something that we can work through with you and explain further if you have any questions. But at this time, we're going to take a look at a live demonstration. Carlos will be joining us now, and then after his live demonstration, we'll be able to answer any questions you might have. Thank you very much.
Okay, thank you very much, Adam. Let's connect with Barcelona now, where I am. Let me try to share my screen. Okay. So let's see. Adam, can you confirm me that you see my screen?
Not as of yet.
Not yet. Okay.
I can see that, Carlos.
Sorry?
We have some delay. We have some delay with some of the slices from Adam, at least myself. So
Yeah.
apologies because of that. Anyway, we will send to all of you the presentation and the recording. I guess the recording will be good. So just sorry about that. So Carlos, anyway, I can see. So I will show my camera too. I can see your screen. I can see the desktop of the SNEOS now.
Okay, good. So let's move on with the live demonstration. Have here on my left the 5-axis system, and we are gonna be measuring a titanium implant. So let me just point the camera towards the system. Okay, that's the 5-axis system, what you see on the screen. So I have two objectives, a 50x objective that I'm gonna be using for roughness, and a 5x magnification objective for shapes. And here I'm holding the titanium dental implant. Let me go to the acquisition software. So let me hide some settings. Okay. So I prepared the acquisition software now to take two topographies in a row and process them and get the roughness values. So if you look here on the top left side, I have a 2D picture of my dental implant. You can see these stripes there. And these two blue or greenish areas are the areas of interest in which I'm gonna be measuring roughness. So these areas correspond to the valleys. So first I'm gonna take a topography there, and then automatically the system will go to the right, to the next valley, and we'll get the results. So let's just acquire, and click on accept the settings. Click on accept the focal plane. So now the system is going to scan from bottom to top in confocal mode. So I'm using a 50x objective magnification in confocal mode. So now we have scanned the first topography, and now we're going to move to the second region of interest, and we are going to acquire a second topography. So now we are doing all the processing. You can look at the bottom left. It says processing. Just have to wait. Now it's computing all these roughness parameters on both topographies. And it's applying all this filtering that we showed on one of the slides, that was shown on one of these slides. So it took about 1 minute. We have here both topographies. Let's open up the first one. This is the topography that we acquire with the 50x and confocal mode. If you look on the right side, we can see a bunch of roughness parameters according to the ISO. So we can see SA of 3.88 microns. Is that the real roughness of this topography? And the answer is no, that's not the real roughness of this topography. Every time we acquire a topography, we we have form errors. In this particular case, I have some tilt. I can see it on the color scale. We have also waviness, and we also have some system noise induced by the system. So we need to apply some filtering and filter out the frequency so we get into the roughness bandwidth. How can we do that? Well, we have a specific operator that's called SA that follow the ISO 25178 standard. If we click on there, we can apply these filtering options that I was mentioning. So we want to apply an F filter, a polynomial of degree of 3. That's what we have found. It works best in dental implants. We can also apply a polynomial of degree of 2. That would work too, but polynomial of degree of 3, it's a good compromise. We have the S filter here and the L filter. So for the L filter, we suggested to apply a cutoff value of 50 microns. Actually, it's not something we claim it's going to work in all cases, but actually it's not something we suggest. It's something written on many papers. So we found that this is kind of a general consensus. So let's apply this cutoff value of 50 microns, and we need to remove system noise. We suggested to apply a cutoff value of twice the spatial sampling of the objective that we are using. Since in this case, I'm using a 50x objective, a good cutoff value would be 0.72 microns. So let's click on apply. And this is a real roughness topography. And now if we look into the SA, we can see that it has dropped down to 0.65 microns. So I would believe much more on this topography rather than the previous one, which included other frequencies that are not inherent to the roughness. So another thing I would like to show you. I'm going to switch to the 5x objective magnification and measure the shape. And I'm going to switch also the technology. As you will see, it's something very, very straightforward and easy to do. So let's go to the 5x objective. Let's change the image mode. I'm going to use focus variation. And I'm going to skip these settings and load a specific recipe to measure in focus variation and with the 5x for this particular sample. Okay, so let's click on acquire. Now we are going to take one topography with focus variation and with 5x objective magnification. So it looks very nice. That's what we obtain. And in this topography, the kind of information that we can obtain is the dimensions. So we can take one profile and we can take one step height from, let's say, from the valley to the peak, which is about 330 microns. We can take some angles if we want. So let's say this slope, it's about 121 degrees. Actually, it's just the complementary. We can take also, we can fit a circle and take some, the diameter, for instance, in this case is 109 microns diameter. So this is the kind of information we can obtain in this case. So as you have seen, I've measured with two different technologies, with confocal first for roughness in two specific locations that I prepared beforehand. So I prepared a recipe, so we can go to specific locations and measure with a specific objective and specific technology. And then after that, what I did was to switch to a different recipe and measure with focus variation to get some dimensions of the outer shape of the dental implant. So that's pretty much all I wanted to show you.